Hello everybody, my name is Roland Kuhn and I'm leading the Akka project at Typesafe. But today I will not talk about Akka, I will talk about going reactive. You have probably all, or most of you, heard about this new term which came up, this buzz which is around it. Well, it was sparked by the Reactive manifesto, which was published last June. And in this talk, I will go through the reactive traits which are laid out in this manifesto, how you can apply them in your design of your applications, and most importantly, what your benefits will be if you do so. The starting point of our journey for discovering this topic is the user. There's always one party which is using the services provided by another. So the user is the starting point from which you always start. You design your requirements for your system, you write down what the user wants to see, and then you go about implementing it. So let's look a bit more in detail what kind of users there are, just to set the stage for what is to come. When you say the user, you typically imagine someone sitting in front of their computer. That's someone using keyboard and mouse to interact with a web browser, for example, reading mails on Gmail. But we're all developers, so we think what is behind the browser. And behind the browser, I mean, this is just a small piece of what a real deployment might look like. Behind the browser, you have a complex machinery which makes all the web go round. The browser talks via HTTP to some server, at Google in this case, if we look at the Gmail app. And this server is called a front-end server, and it will take the requests from the browser, and it will eventually respond. HTTP request response. So the browser is a user of the services provided by this web server. But this web server is called a front-end server for a reason. The reason is that it's actually hiding all the back-end services which are providing the actual services consumed by the user. So this front-end server will use an internal service. For example, if you are in the Gmail app and you hover your mouse over an email address or a name, there will be this little pop-up which comes, and this pop-up will contain contact information for the person and probably also a little image on the left upper corner. This image needs to come from somewhere. So what your web browser does is it dispatches a request to the Gmail front-end server. This will find out, okay, this is an image I need to fetch. It will contact an internal service which is responsible for getting these images, and thereby the front-end server is a user of the internal service. This internal service will, in turn, make use of some storage engine. Could be a distributed file system or a key value store or what have you. So this internal service will go to the storage, tell it, give me the bytes which make up this image. Thereby, this internal service will be the user of the storage service. Then the bytes will travel back all the way into the browser where they will finally be rendered on the screen as this image. This is an example of such a request. Other things, when you log in, you get all your emails, your labels, your contacts, the whole layout of the page. So there will be many different services which will have to collaborate in order to open this Gmail app. And some of them will talk to databases. Some of them might even be external. I have never worked at Google, I don't know how it really works, but I imagine when I get a mail notification from Stack Overflow, there appears this Stack Overflow icon on the upper right. That might well be an example where the Google front-end server calls out to an API provided by Stack Overflow to give me the content of this little call-out box to the upper right. So this is just one example. I mean, in the end, every service is created for the purpose that it's consumed by some user. What is the single most important quality that a service must have to be useful for the user? It needs to respond to requests. It needs to be responsive. Because when you send a request and you don't get a response back, what is your conclusion? The conclusion is that the service is probably currently not working. It's unavailable. And we have become used to all services that we consume being basically available 24/7, all the time. We want them ideally to be always there and free or nearly free and high performance and snappy and everything. But most of all, it needs to be always on. Imagine you're using a flight booking website and you start entering your data and the service does not respond anymore. What do? Well, there are alternatives. You go to a different site. You do not spend your money on that site which you find is unavailable, because the conclusion then is that you think the provider of that service is unreliable and you don't want to book your flights at a site which is unreliable. So in order to stay in business, you need to have your services always on. The next thing is, there's only so much time you let pass before you become frustrated. So when I log into Gmail, it takes a few seconds to download all that JavaScript, get it started, get it booted up. I'm used to that. But after that, when I click around and use the keyboard shortcuts, I expect things to be nearly instantaneous. We're a pretty spoiled bunch there, because today everything is so fast, when something doesn't happen immediately, we get annoyed. So if I'm on a slow internet connection and I click on the inbox and it takes a few seconds to get the emails, I start being annoyed. In this case, I cannot really switch because I have to use Gmail, but in other situations, we will just switch providers to those which are more responsive, which are more interactive. And talking to a real user, real human user, is not even the high end. For us, something feels really interactive if the latency of the response is below 100 milliseconds or something like that. And we start being annoyed at 1 second. But if you go into, for example, the other end, which is high-frequency trading, the algorithms which place and cancel orders all the time expect the system to respond on a sub-millisecond or even microsecond scale. The algorithms themselves must respond to changes in the market on that time scale. So there we are entering near real time. It means our service needs to always respond within a maximum time. And well, if that is not possible, that should be really the rare case. Yeah, we must not miss responses, and we must deliver them timely. So this is the topmost, the most important quality of a service. And the rest of this talk will be just about how we get there, how we implement that, and how we benefit from that. So the first one is, we have a request going to a service, and we have a response which needs to come back in a timely fashion. Another word for that is that the latency of the response needs to be bounded. How do we realize that? How do we make it such that the latency does not really spread too much? So in almost all cases, it should be, say, below 100 millisecond. And how do we keep that bar pretty high, or the latency low? So the first one is, think about what your service does. You have here the process. I've just put 3 yellow boxes as tasks to be performed between the starting point, the purple one, and the finishing point, the green one. When you want to render the Gmail app UI, for example, the front end at Google will have to go to many different places to collect all the information which you need there. You need to get the email headers, you need to get the labels, you need to get the context, you need to get the CSS, all the images, and so on. So most of these can actually be done in parallel. So what you should do first is you should start using parallelism where it is available to you. So instead of adding the 3 latencies of A, B, and C, when we perform the things in parallel, we can get down the latency to that of the one task which takes longest. Because in the end, we will need all 3 results in this example to compute the final response, which gets sent back to the client. So we cannot get below the latency of the task which takes longest. But this is very important, because you could have like 100 such calls. And if you collapse that to 1, I mean, you've gained probably 1 or 2 orders of magnitude in latency by using parallelism. What this means is that the framework which you're using needs to provide the facilities for doing so. When we do this, we need to asynchronously start the tasks A, B, and C. The normal thing is you call a method, you get the value for A back. You call the method for B, you get the value back. It's all one after the other. If we want to do them in parallel, that is no longer possible. The method cannot return the value. The method can only return a future. The future is the promise that there will be, at some point in the future, the result. So what this method could do is it parses the request, figures out I need to do A, B, and C, and it creates the futures for those. Now what do? If you are using Java util concurrent future, you will have to block to get the values out. You can only call .get on them, and still, I mean, you have done them in parallel, but you needed to block to get the results and formulate the overall response. What is much better is if you use what we call composable futures. They will be part of Java 8 as well, known as completable futures, but you have probably seen them before in implementations like Netty, which has the listenable futures, or in Scala and Akka we have our own composable futures. The trick with those is that the last part here, this green dot, which means assembling all the parts and computing the final response, that is not something which you need to do on the original thread anymore. You can just describe how it should happen, given that I have the results A, B, and C. And you put that as a callback onto these three futures. When they are all done, it gets executed. And then this completes the future which you got back from this composition. And you use this future to complete the request from the client in your framework, in your web framework, for example. This means that the framework needs to be able to deal with the way that you invoke something, and what you get back is not the value straight, which shall go straight to the client. You get back a future for that. And once that future is completed, you hand it back to the client. What this does is it turns this process from being synchronous and blocking invocation on a single thread into being event-driven. When this request comes in, it triggers the execution of A, B, and C, which will run asynchronously. When either of these completes, that's an event. On this event, you can install an event handler, which handles whatever shall happen next. So once A, B, and C are all done, the event handler will compute the overall result. Then, when that is put into the future, the framework will have installed an event handler, which sends back the response to the client. What have we done here? This is quite revolutionary, because if you look at the original picture, like this, we have taken one thread which was used all the time, even though A, B, and C might have been computed on a different host. But while this request is being processed, one thread is held hostage all the time. So how many threads can you start on JVM? It's probably something like 10,000, give or take. You can sure not start an order of magnitude more. If you actually try to do that, you will see that this has enormous overhead. A thread is a very expensive object which needs several megabytes of memory, and the system scheduler will have hard work to do figuring out which thread to run on which CPU if there are so many of them. So this will have a tremendous overhead. If we go to the solution where we parallelized in an event-driven fashion, this means that what the threads are doing is they just compute what needs to be done and describe what shall happen later as work items to be attached somewhere, and it frees up the thread immediately. So instead of being able to handle only 10,000 concurrent requests in your system, because that's the maximum of your thread pool size, you can handle a lot more requests with just a handful of threads, because you basically only need one thread per CPU core, which you dedicate to this purpose. Now, you have taken care of that the business logic is properly parallelized, and you have reduced the latency by doing so, and everything is nice. But what happens if your system gets pushed to the edge of its capacity? So more concurrent requests come in, and there is only finite CPU resources, and requests will pile up will be queued in some sort, for example, in TCP buffers or TCP connections, or even explicitly in your application. In that case, once the latency rises above the point where you violate the expectation of the user, your service effectively becomes unavailable. How do you make sure that that does not happen? You can use a trick from electrical engineering, and that is a simple circuit breaker. So what you do is, work items come in from the left here, and you normally perform them. That might be a web service call, it might be an expensive computation, it can take some time. The important thing is that you monitor how long it takes. And once you are in danger of violating your latency commitment, the circuit breaker will trip. And by tripping, it goes to a different mode, where you cannot handle the full process at the full rate anymore because you hit the limit. So you need to do less. I called it fail fast. One example there is that you simply respond to the client in that case with a 503 service unavailable. Temporarily, this server is overloaded. This would be suitable, for example, in the example I gave with this image in this little pop-up in Gmail, because if that service, which gives you the bytes for these images, is currently overloaded, for example, or it might even be unavailable due to other reasons, then if you put this circuit breaker in, still the response will come back into your browser. The browser will go on happily rendering the page, just the image will not be there. You can still read emails, you can reply, everything. The images are missing. That might be completely reasonable. The service of the whole site is a bit degraded, but it still works. It's still responsive. Another thing is if you compute something in a certain level of fidelity, you can decrease the level of detail under those conditions where you max out the CPU, for example. So the thing is, you can use a circuit breaker to gracefully degrade service instead of failing completely for everyone. That's the basic idea. The next thing which you can use to a very similar effect becomes available if you treat events as flowing through your system, and you keep and you model these flows of events explicitly. What you need to do there is you need to place events in queues. And once you do that, there's a whole field of theory which you can apply, the queuing theory. You can design your queues to fit all these purposes. You can have prioritization of certain events. But the most important one when it comes to latency is that you can use bounded queues. There's this very useful formula which is called Little's law. Little's law describes when you have an average incoming rate of items into your queue and an average processing time for each item by the thing which drains the queue, then you can calculate the average queue length which will form in front of this service as the product of the rate and the processing time. It's quite intuitive. A corollary to that is if you take the queue length and multiply it by the processing time, that is the average time an element needs to wait between being queued and being dequeued. So that is the latency introduced by the queue. If you choose to bound the queue size to a certain value and the processing time stays constant, that is very important here, the average processing time must stay constant, then you effectively put a bound on the maximum latency for the queue before that service. What do you do when the queue is full? Do you use a blocking queue and when it's full it will just block? Of course not. You need to do the same thing as for the circuit breaker. Service is currently in a condition where you're about to violate your latency requirements. So you need to drop something. So when the queue is full, you just go into this fail fast mode, just as for the circuit breaker. You can hand your work to a different service which offers lower level of detail or any of these possibilities. All this traffic shaping within the machine, this event flow shaping, is only possible if your system is event-driven from the bottom up. If you model events flowing through your system, you have very nice tools available which you can apply here. Now, we have designed a system such that under blue sky scenarios, and even if more users come and so on, it still keeps the boundary, the bounded latency constraints. But that is not all that can happen. We know that. Many things can go wrong. The software will fail. We all know that. I mean, who here thinks that they can write perfect software without flaws? I hope no one raises the hand, because I would call them a liar. That is not how it works. So it will always be this exception which you don't catch, or this case which you didn't foresee in the algorithm, or you try to load balance things but by sending them between services, but you might introduce a flaw in your algorithm and have a live lock, actually, or you might introduce deadlocks. In those cases, the service will not respond. Other cases are, and that was the most frequent one when I was an administrator still, were power supply failures. When the power goes down, the computer is not available anymore. It doesn't matter how perfect your software was written. It will not respond. There are other possibilities. Disks can fail, we know that. A fan can fail, which leads to a CPU failure, or memory corruption can lead to a kernel panic, all these things. They are not really under your control. They can happen, and you need to build the knowledge that failure can happen into your model. And the last and very important point is that humans can also fail. There was a study which was conducted, unfortunately I forgot the name, about failure in IT systems. 2004 it was published. And they did a test. They had a RAID 5 system with one failed disk and tasked a technically savvy and trained person to replace it with no stress and no bringing customers and everything. But still, in 10% of the cases, the person replaced the wrong disk. What happens to a RAID 5 if you do that? You have one failed disk and you take out one of the good ones. You destroy the whole array. You lose data. And that's caused purely by human error. Another classical one is the cleaning personnel just needs to plug in the vacuum cleaner somewhere and unplugs the server. Everyone has probably seen that in action before. So what do you need to do to protect against these failures? What we want to achieve is that the system still keeps responding, even if things go wrong. We call this property resilience. So even if you hit it hard, it will retain its form and shape, or it will recover quickly after being deformed. That's what resilience means. Well, you will need to go distributed. For most of these failure scenarios, it helps tremendously if you spread out the risk. If you do not have one single point of failure for anything. I put 3 computers here. That could be servers, that could be racks, that could be computing centers on different continents, it could be different teams running things. The point is that you need to spread out the risk in order to mitigate it. Probably all know that. Now, what happens if you distribute a computing system? What happens if you distribute computation? Well, we talked about it already during the fan-out. When you want to do things in parallel, you need to execute them asynchronously. When you want to distribute things across computers, they will run asynchronously. I make the request here, send it to that node over here to compute something. It will run it in its own time. I'm over here, that's there, decoupled, asynchronous. Now, what happens if an exception is thrown in this task over here? Normally, when we just run blockingly on a single thread, we just put try-catch around it and catch the exception. But that only works because the execution happens on the same stack below the method call we just made. But if that actually happens over there, that doesn't work. It's not available. The question is this a good thing or is it a bad thing? I would say it is a very good thing because it keeps things isolated. It helps in compartmentalizing failure, in keeping failure from spreading. The philosophy here comes from shipbuilding, where you can put bulkheads between different sections to form compartments. So when this tanker here hits an iceberg, for example, or reef or something, it might penetrate the hull in several places, and some of these compartments might run full. But since they are all isolated from each other, this will not affect the whole ship in a way that it will sink, unless it's completely ripped open, of course, right? So if you can contain the failure to certain compartments, the ship will stay afloat. Now, you might have heard of a very famous case for this. That was the Titanic. The Titanic had a design which was, I think, new at the time, that they had these bulkheads in. They had these compartments, which is why they call the Titanic unsinkable. We all know what happened. It sank nevertheless. What you can learn from that example is that is bulkheading going terribly wrong. Because what they did is they put in these compartments, but the bulkheads didn't go high enough. So when the Titanic hit the iceberg, the first 2 or 3, I don't remember, compartments were ripped open and ran full of water. That should have been fine, but since the bulkheads didn't go all the way up, the water flowed over into the next compartment. And then the ship sank even more, and it flowed over. And one compartment after the other was lost until, well, the Titanic was on the ground of the sea. This is something you might have observed already when you run deployments of application servers. You have cascading failures, at least if you don't protect against them. An example, you have a load balancer, you have 3 application servers. Over here, one of them has a problem, starts being slower maybe, starts being overloaded. The load balancer will take that one out and will not route to it anymore. But the 2 here will now see 50% more traffic than before, which might just knock them out because they are now overloaded. This is a cascading failure because the bulkheads were not tight. So, something has failed. We have it contained in its compartment, which means the failure went somewhere. But we're looking first at what the user sees. What will the user see of sending a request to a service which fails during that request or which is currently unavailable? It will simply not get a response back. There is nothing the service can do. If it's really failed, it cannot continue. So what the user of the service will do, it will set a timeout. And the nice thing is, we have designed the service such that the maximum latency is bounded. So once you exceed that bound, you can put in some padding to round it up or something. But if it's like 100 milliseconds beyond the allowed limit, you can just declare it a failure. And that's that. The user only sees that the service does not respond and will not respond, probably. So that's the decision made. There was a failure. And the service which used that other service can happily go on and decide, for example, not to draw this image in the Gmail app and still answer the request saying, okay, this is the pop-up, but I don't have an image right now. But what happens to the exception? The exception which was thrown in the other compartment. It is someone else's exception, so we should also make it someone else's problem. This is the important part, and that is the principle of supervision. Supervision works a bit like this. You have this blue thing here, that's a hypothetical service. Request and response flow in the horizontal plane, and failure goes upwards. Now, when I say failure, I should probably talk a bit about the difference between validation and failure. If I send an invalid request to a service, is that considered a failure? No. The service will just validate the request and say, your request is crap, don't give me that. And we'll send back a response. So there's a request, response, everything is fine. So validation is not a problem. But failure is when the service cannot continue to perform its duty. When this is supposed to talk to a database and database connection goes away, it cannot perform anymore. So the failure needs to go to some other place. Let me give you one other metaphor to motivate what shall happen. Let's say you stand in front of a vending machine. Vending machine here, can of Coke inside, which you want to buy. So you put the coins in the slot, and then you press the button. I want some Coke. Now, several things can happen. The first one is you didn't put in enough coins. There will be a feedback. That's a validation error. You didn't put in not enough credits, or the Coke might actually be empty. Well, out of Coke exception, so to speak. But if it all works, you get your can of Coke and are happy. But what if the machine actually cannot do that fundamentally? The logic board in it might be broken. Then it can't respond. Or someone might have put chewing gum in the slot. The coins can't fall down. The machine cannot really cope with that because it doesn't have a chewing gum sensor. So it will not even give you useful feedback. The machine will just not work. Or trivially, it might be out of power. So when you see a machine that is broken, and you go there and you want to buy something from this vending machine, and it doesn't work, what do you expect? What shall the machine do? Are you supposed to handle the failure? Are you supposed to pull out a wrench and open the machine and repair it? No, that's not how we operate. I am the user of the machine. I want to use its services, but I am not the operator of the machine. The operator is the one who is supposed to keep the machine healthy and in shape and capable of servicing my requests. So what we expect is, and maybe there's a phone number on it which I could call, but what we actually want is someone looking after the machine, maybe even with automatic monitoring, and then someone will come, a repair guy will come and fix it. That is the supervisor. So this is the important lesson also in software design. When you invoke an API, you cannot be held responsible for how to fix that service if it encounters an internal failure. This is what I think is completely wrong with catching exceptions from a different service module. Because then by catching exceptions, you basically are the only one who can handle it, because you are the only one who saw the exception. No, the exceptions should not go to the user of the service, they should go to its supervisor. If you use actors, for example, well, every actor has a supervisor, but every implementation of reactive techniques has a different way of handling that. The important point is that there is always this one thing above the service, which is concerned with keeping it healthy and running. If you look at what is happening here, we pass requests in, get responses out, and we need to communicate failure, but they're with different partners. We have the user and we have the supervisor. This basically means that the service needs to be event-driven, because it must react to events as well from the user as from the supervisor. One very useful property when implementing that is if your reactive framework or implementation is location transparent. What does that mean? I have a service here which uses another service over there, and if the way of sending a request from here to there hard codes the location of where I'm sending and the way I'm sending it there, I will have a very hard time switching that out. So if that machine goes down and we have a supervision process which will spawn another node, for example, over here, it will be very tough to make use of that. Location transparency means that the mechanism of getting the request from A to B and the response back does not care where the service lives. So you can transparently switch out the broken service by a new functioning one. And that gives you seamless resilience. Now, you've built your system, you have properly engineered all the latency bounds and made it resilient against failure, and it's an awesome new app, and everybody loves it, and soon the internet at large will discover it. Might be on Slashdot, Reddit, Y Combinator, it doesn't really matter. At some day, people discover it, and then the herd comes thundering towards your service, and they will hit your service. They will hit it hard. And then what happens, if you didn't prepare for that moment, is that all your careful engineering will just lead to lots of pages which say, we are currently unavailable. We can't service your requests. We're under heavy load. We can't take it. That is not what you want to happen, because just at the moment when you got successful, you want to show the world how awesome you are. So, what is the basic requirement, the first one which you need to build into your design in order to cope with such situations. It is that the incoming work items to your system, the requests, need to be partitionable. If you build in something like all requests must go through here to be authenticated, authorized, for example, or whatever, then this thing will define how many requests per second you can handle at maximum. You cannot go beyond that. So once you hit that, you hit a hard limit and you can't scale further. What you need to do instead is you need to make sure that you can partition your incoming work stream across multiple nodes so that you can add them at runtime, preferably. And if you have an expensive computation to be done by this service over here, you want to make it so that you send to that, it could be not one node, it could be 10 nodes, and then you round robin across them to spread out the load, to handle higher load. Because what you want to do is you want to react to changes in your load by scaling up and out, as well as down and in. Once you have a load spike, what you want is you want to ideally, for example, double your capacity within the next minute. Because something happened, you were on Reddit and everyone's hitting your site. You want your service to continue functioning. If you happen to use Google Compute Engine, we have tried that out. You can add an Akka node to a cluster in about 20 seconds. That is real flexibility. That is elasticity. And we'll see more of that in the future because demand for that is there. So you've scaled up, you dealt with your spike, but you also need to scale down because if you keep these 1,000 instances running just because that was the maximum you ever needed, that will be extremely expensive. You don't want that. And in order to do that, you need to monitor your system. You look at the queue sizes, the latencies, the CPU utilization, and when you hit certain thresholds, you scale either up or down. One thing which is, in this case, not a nice to have, but a requirement is location transparency again. Because if you send to a service and you want to scale that out, then you need to make sure that the clients using that service can still reach all of these nodes. So they fundamentally must not care who processes it. It must be transparent. You send to this name, so to speak, and then you bind this name to, say, 10 instances or 100 instances to fan out the workload. If your mechanism of sending messages was not location transparent, you will have great difficulty doing that. And of course, all of that only works, the monitoring part, the scaling part, the location transparency part, works only if your platform is event-driven underneath. Now, if you apply these things, that has some interesting consequences. If you think about a distributed system, and you think about the consistency of that system, that means if I affect a change over here, what are my guarantees of seeing that change reflected in that other part of the system? Are they always in sync? Will they always know the same thing? Will they be consistent? Well, we know that distributed transactions don't really work. They don't scale. And the reason for that is, if you have a system which has a certain size, like 10 nodes, they will need to communicate amongst each other so that they are sure, yes, we are all on the same page, you can continue. Consistency has been achieved, you can continue. Once you grow the system, the effort needed for maintaining consistency will grow quadratically with the number of nodes you have in there. It will be very much effort to make the system larger, and that destroys the benefits you have from trying to scale it up. Because instead of adding new nodes which just add to the computing power, you basically take away CPU cycles by all this coordination overhead. One example which is often used to discuss consistency are bank accounts. And one example I would like to give for eventual consistency, which is what happens if you relax the constraints a bit, are ATMs. When you stand in front of your ATM, put your card in, enter the PIN, and want to get your money. And there's currently maybe a network hiccup. And the machine says, I can't give you money. Doesn't work right now, I don't have connection to the server. That doesn't really work. Your customers as a bank will be very annoyed by that. They will not like that. Because when I go to an ATM to pull money out, I'm pretty sure that I have the money in the bank account. And the only reason the machine would have to reject this, it is because the machine cannot currently check the balance of that account. What the machine can do is check that the PIN matches the card and so on, and that thereby identify me. I say I want $200. The machine can just give me the $200. The machine will store the information that it has given me $200 that can be persisted. And once network connectivity is restored, it will send that information to the central server and update my account. Now, what if my account goes negative? In that case, I should not have received $200, but I got them now. Well, there are two answers. The first one is that all society has ways of forcing me to give back the $200. But that is probably not what the bank will do, because it leaves a bad impression. No, when my account goes negative, I will have to start paying interest. So the bank actually earns money from that. So the ATM being not always perfectly consistent is not really a problem for the bank. Think about that for a second. There are different examples which you can think here. The point is that strong consistency is not nearly as important as you might think it is. Eric Brewer has thought about these issues in distributed systems and consistency 14 years ago and published the so-called CAP theorem. This CAP theorem can be paraphrased as you take consistency, that's the C, availability, the A, and the possibility of network partitions, that's the P, and you can pick only two of those. You cannot have all three at the same time. That's one way of putting it, and one way of interpreting that is, well, I cannot really opt out of network partitions because they just happen, they are outside of my control. So during a network partition, I need to choose either I am unavailable or I am inconsistent. That might be one way of putting it, but it's not quite the truth. Because what the CAP theorem actually says is that you cannot be perfectly consistent and perfectly available at the same time during a partition. But you can get as close to that as you want. You just can't reach the perfect state. And as I told you with the ATM, it is not always needed to have perfect consistency and perfect availability. If you look at the link I give there, that's work by Peter Bayliss on probabilistically bounded staleness. It's a nice website. There's a paper you can also read, which investigates a dynamo-style database and looks at, given certain speed of propagation of reads and writes within the replicas, how likely it is that after a given write, you wait some time and then you read at some random replica, that you see that write. Basically, it answers the question of how consistent and how eventual is eventual consistency. And it turns out that with modern systems where all of these time constants are in the order of 10 milliseconds or 100 milliseconds or so, if you wait 1 second after the write, you're very likely to see a fully consistent system. So ask yourself again, is it really necessary to have full linearizability, full perfect consistency at all times? Is it worth the cost of not being scalable? And Reactive clearly answers, it's not worth it in almost all cases. When you want to design a system which is eventual consistent, the one constraint you have is that, well, eventually it becomes consistent again. So the ATM will eventually deliver all the updates when network connectivity is restored. When you design systems like that, you have to think about how to disseminate information, how to gossip the state of the different parts of the different replicas in your system, for example, how to do heartbeats, detect that someone is down, unavailable, and so on. And all of this is naturally expressed as events. You send a message via a socket, that's an event. You receive the message on the other side, that's an event. All of that is naturally event-driven. And it helps a lot in implementing these things when you work on a foundation which is already event-driven. There are some corollaries to all this. And one of them is, if you have designed your system nice, with considering responsiveness, resilience, scalability, everything is event-driven and so on. If your main focus in this application were like a blocking database call here, it will destroy the whole thing. It will fall over. All the nice properties will be lost. Reactive really needs to be applied all the way down, from the upper layers in your JavaScript of the client side of your imaginary Gmail app, down to the database. If you do everything using these principles, well, then you can have these nice properties all along the way and everything will just work. But I realize when I say that it's a bit of a futuristic requirement, because we're not there yet, to be honest. If you, for example, look at databases which are widespread, SQL databases, they do not have asynchronous APIs. You cannot use them in an event-driven fashion. There are some stores like MySQL, Postgres, where there are APIs emerging. NoSQL stores have had that for a while now, but the big masses are not there yet. Another thing is, if you have a sizable project, you will always have different teams, different languages, different toolkits for implementing things. And if you want to be reactive all the way down, then all of these toolkits need to cooperate. They need to all support the reactive exchange of events. So reactive needs to be polyglot. And that requires collaboration between different parties. One example is that we as Typesafe are currently collaborating with others in the field to create reactive streams. Heavily inspired by RxJava and will be usable to exchange events in different parts of an application in non-blocking, fully back pressure aware and nice fashion, fully reactive. But this requires a collaboration between different parties, obviously. So we've looked at the user and the service and what the service needs to do to satisfy the user. But what about us? What about the developers who write these services? First of all, this is not just minor incremental change. You need to think differently about how you design your applications. I've been asked at the booth, and it's true, you cannot just replace this tiny piece in an existing application over here and make it reactive. You will not be able to reap the benefits. You need to really think differently. And it can require a leap of faith. I've seen that myself with a team of seasoned developers who had difficulty believing that if my precious thread, if I don't do things on this thread, if I let the thread go, things might not happen. What you need to learn is that you can trust the machine, that if you spawn something asynchronously, it will eventually run. It will actually work. Also, you will notice once you do that, for example, once you send messages using actors, you will not have nice stack traces anymore for debugging. You will not be able to step through your code, simply because there are these boundaries where you spawn things off in an asynchronous fashion. And step-through debugging will not be the weapon of choice there anymore. There are advances which are being made, but I think, especially when it comes to the debugging responsiveness issues and so on, that we will see more like logging-based debugging solutions which allow you to step through the application after it has run, after it has been recorded. But what this means is services are decoupled from each other at runtime. which due to the execution model, but they will also be decoupled in the program, because you cannot depend so much on different parts. You cannot share so many things, which gives you loose coupling. So you have simple building blocks, which you write, which due to supervision have clean separation between business logic and failure handling. You have these distributable pieces of work which you can send messages to make them perform the computations you want. And once you have done that, you have these loosely coupled elements, which the runtime you choose can run in parallel if there are enough cores and so on. Nice possibility for parallelization. But what this forces you to do is you can make less assumptions in how you write the code. You cannot share as much as, I have this thread here, I control what runs when, here's a variable, I use it here, doesn't work anymore. But by having less assumptions you can make, you have these components more independent from each other, which lowers the maintenance cost if you need to refactor later. But the most important thing, which brought me to actors in particular, is you have these tiny little things which you can program, which have a life of their own, which you can play with, and they're just fun to work with. And that was also feedback I got from the Reactive Programming Coursera course. Now, I will conclude by showing the slide which gives you the 4 reactive traits. We've worked through responsive, resilient, scalable, event-driven, and all of that is what is reactive programming. Thanks a lot. Unfortunately, my timing was a bit off, so there was no time for questions. You can come to the Typesafe booth, which is just outside to the left if you have questions. Thanks a lot. And there's a talk by James Roper at 4 in room C1 about about reclaiming discipline in client-side web development. Thanks.